Imagine you have something, like a ball or something like that, maybe this catch ball, and it's released. So the weight of the ball is an external force. And I've said this before, it's coming from the earth or something, and it's reaching out and pulling. And a force is a vector. And that's all we're talking about in chapter 3 is vectors, vectors, vectors. So every vector has a magnitude and a direction. So what is the direction of the weight? Okay, survey says, responses. Ooh, it's a toss-up between south or some mystery direction that makes an angle of 90 degrees with respect to all 4 of those directions. So what I'm trying to do is just remind you that I guess that in life is 3-dimensional. And so there is a word for the direction that the beach ball falls. It's called down. And so north is that way, south is that way. So balls don't fall that way, they don't get pulled to that direction. Make sense? It's 90 degrees away from south. So this one is it's not a multiple choice question. What it's going to be showing you on your screen or on your phone or something is asking you to click your finger on where you think, I guess, the tip of the sum vector is. Just like I did in that animation thing, you've got these 2 vectors starting from the origin. The sum of u plus v, if it starts from the origin, where should it end up? That's cool. It's sort of a heat map or something. And where I wanted you to go was this sort of little circular region somewhere up in here. And you can get there by kind of imagining that if I'm doing u plus v. So if I took this v there and kind of moved it up there and connected the tail of it, well, it goes left, 1, 2, 3, and up 2. So 1, 2, 3 to the left, up 2, so it should end up there. That's where the new v would be, right? You've got these 2 new vectors, v and u, and I want you to subtract them, u minus v. And note that subtracting a vector is the same as adding the negative of that vector. So u minus v can also be written u plus negative v. So your steps here would be, first flip the v vector to find where negative v is, and then add it to u, and then try to click your location of your difference. This is a vector difference. 541 responses. Look kind of like this. You see people are kind of clicking around on what they see, but you want a lot of the heat's out there, and then am I correct? So I'm looking for something in this region. So the way I would do it is the negative v vector is just here. That's negative v. And then I'm going to take this vector and shift it over and put it on the top of that. So I think it goes something like that. Negative v. So this vector now, from here to here, is u minus v. It's the difference of these 2 vectors. What I have is a demonstration here where I have 2 balls that are rolling on a pretty frictionless track. And path A is that it just goes in a straight line. Path B is that it goes down the hill and up the hill, and then also ends up in the same place. And so the question is going to be for you to predict, and the other thing is that there's a spring-loaded launcher over here, which hopefully they can stay you, so that when I pull the spring, they both get launched with the same initial velocity. And I put the red one or the pink one in front on A and then the white one on B. So we're going to load it up again. I think the video just shows the end of the track over there. But let's see. And remember, the pink one is A and the white one is B. Watch carefully. Mark's cassette, go. Should we do it again? maybe it was the balls. Maybe we'll switch it up so that A will be the white one and the pink one will be B. Let's do that. Then I'm going to ask you to observe. So that, you don't want to stick. You keep rolling off the, oh, there we go. Okay, good. I'm glad. I saw B as well. Not everybody did, but that seems to be the experiment. So B seems to win every time, and I found that it doesn't really seem to depend on the exact shape of the track. There's lots of different ways of making this, but the lower path tends to win here. So maybe you could pick an explanation from this list that makes sense. I think 4 of them don't really make sense, and one of them I like a lot better. This one, I've given this demonstration to actually a room full of physicists at the Canadian Association of Physicists, and it kind of comes out the same. A lot of people predict that they'll end up at the same time. So don't feel bad. The B is the explanation I was liking. But basically, B is always trying. So they start off with the same speed, and then I think what happens is that the one that takes the lower path is going faster. It's because it was rolling down the hill. And there's even a component of the normal force here, which is pushing it in I guess, the plus x direction. So that while this one's on the lower path, it's going faster than the one on the top path. Then, because it's coming back up, there's going to be, I guess, a negative component of the normal force, which will slow it back down, so that it'll end up at the same speed that it started with. But it's ahead. So this one never has a time to catch up. So it wins every time. So it's kind of a difference between they both go slow, and then there's fast, slow, and then slow. So you can go slow, 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 or slow, fast, slow. It's sort of better that's why it always gets you there sooner on the lower track. You've got 2 balls, and at time t equals 0 or something, they're both released, and one is released simply by dropping it from rest. That's ball 1, and the other one is released with this spring launcher, which launches it with a horizontal velocity, so it's going straight sideways. And the question is, which ball will hit the surface first? Assuming that below there is some sort of horizontal flat surface. Both at the same time. So it's kind of amazing to think of this. But I think of it in terms of the components of the initial velocity. So here, v0x, the component of the x velocity is 0, and v0y is 0. Here, v0x is some large number. It's going a lot fast to the right, but since that velocity is fully horizontal, like in the x direction, v0y is equal to 0. So if you're just thinking about the y component of the motion only, then they both have the same initial y component of the velocity. It just, the top one lands way farther away. It certainly goes a lot farther, but all that motion is in the x direction, and the y component just falls down. So a tennis ball is launched at an angle. It flies through the air in a parabolic path, A, B, C. So for A is just after I let it go, and C is just before it sort of reaches that same height again. So it's like A, B, and then C. At point B, is it that the velocity is horizontal and the speed is maximum? The velocity is horizontal, the speed is minimum. The velocity is horizontal, but the speed is neither maximum or minimum. Velocity is not horizontal, but the speed is minimum. Or E, the velocity is not horizontal and the speed is neither maximum nor minimum. So it's sort of between B and C. Velocity is horizontal, speed is minimum. Velocity is horizontal, and speed is momentarily 0. That's different than what it says on the screen over there. Sorry. Well, anyways, the answer is B that I was looking for. So anyway, the speed's not 0. That's my point. 0. And this is the thing. So what's going on here is that the y component of the velocity is 0 up here. So here you have, what you have to do is always kind of think of this velocity as having these two components. The real velocity is this one, and then you've got v0y and v0x. Up here, you've still got the v0x, because that never changes, but at this moment, vy is 0. And so if you're looking at the Pythagoras or something like that, the v is equal to, absolute value of the v is v0x squared plus v0y squared. But up here, the thing is just vy squared plus, which is 0, plus v0x squared. So at this moment, it's just the absolute value of v is just v0x. So it's a minimum. That's as low as it gets. And then it starts to increase again after that. But it's certainly not 0 at the top of the path. So my daughter's monkey, stuffed animal, is hanging by an electromagnet right now up over there off the, if you can see it, off that balcony. Do you see him? I am not sure what this monkey's name is. I need to ask Elizabeth. But she just called him Monkey, and I got her, she's now 29. She donated this monkey to the physics demonstration bin, and John found it. And what he's done is he's hung the monkey from an electromagnet up there. And the wire comes down around here, up here, and is then connected to a beam, an infrared beam. And if I break the beam, then it turns off the magnet and the monkey falls. The question is, so the classic problem is the monkey is hanging from the branch of a tree, is spotted by a hunter. The monkey sees that the barrel of the tennis ball launcher is pointed directly at him. So there's a laser pointer on there, which I think, I don't know if you're able to show that the laser pointer is aligned. Yeah, see the red dot? That red dot is parallel with the initial velocity of the tennis ball, and it's aimed right at him. Yeah, sure, go ahead. At the instant when the gun is fired, the monkey lets go of the branch. Predict, the tennis ball will go above the monkey, B, below the monkey, or C, hit the monkey.
Okay, it's armed, it's ready to go.
Okay, 3, 2, 1, go! Oh! Missed it by that much! It's pretty close though. So it's supposed to be C. I think I put that on the thing. Had the monkey stayed on the tree, the ball would have curved under its target as gravity caused it to fall a distance 1/2 gt squared below the straight line. But 1/2 gt squared is also the distance the monkey falls while the ball is in flight. So yes, the tennis ball in this case hits the monkey. A mouse digs a tunnel 1 meter down, and then he turns and continues digging 1 meter east, and then he turns left and continues digging 1 meter north. And the question is, how far in meters is the mouse from his starting position, that displacement? Responses sort of went around. I liked square 3 meters. And the way I did it is, first of all, I imagined like a side view, I guess. Since I can only draw things in 2D, I just imagine like I'm looking at the side. So he goes down 1 meter, and then he goes east 1 meter. And then what I think, so you can get there that he goes square root 2 meters and that first kind of thing. And then I'm trying to imagine that he goes this distance and then turns a perpendicular direction. And then there's this whole perpendicular. So this is, I don't know if this is looking straight down or not, but I feel like that last leg, since it was perpendicular to the east and perpendicular to down, will be perpendicular to that square root 2. So you get square root 2 squared plus 1 squared. you get square root 3. Factory conveyor belt rolls at 3 meters per second. A mouse sees a piece of cheese directly across the belt, and so I guess relative to the cheese or the belt or something like that, the mouse just runs directly towards the cheese. But and so the mouse's running speed is 4 meters per second, and that's relative to the conveyor belt, I guess. And the conveyor belt's moving down 3. What's the mouse's speed relative to the floor? Yeah, so that looks pretty good. But yeah, basically you've got the 4 plus the 3. This is the velocity of the mouse, I guess, relative to the conveyor belt, plus the velocity of the conveyor belt relative to the ground. It's going to give the velocity of the mouse relative to the ground. So it ends up being, I think, oops, got this kind of messed up here, 3, 4, 5 triangle. This is square root of 3 squared plus 4 squared is equal to 5. You have a pebble that's dropped from rest off a high balcony. You know its acceleration. You know the time. Somehow you time it. And you want to know how far it went in that time. Which of these 4 equations would be your starting point? Easiest one to start with is equation B. I think that's right. So, and the reason is that the implicit thing here you don't care about is, I think you don't care about the final speed just before the pebble hits the ground. So that's the equation that doesn't, this contains final speed, all of them contain the final speed, but not equation B, so that's a good one there.
A small airplane is flying east at 220 kilometers per hour relative to the air. I'll call that plane relative to the air. The wind is blowing towards the south at 85 kilometers per hour. That's the air relative to the ground. What is the plane speed relative to the ground? So this will be the velocity of the plane relative to the ground. And so I think I'll just use the Pythagoras since these are at right angles. 220 squared plus 85 squared to get that speed. Take the square root of that, and you get 236 kilometers per hour, which is D.